Between the brilliant stars and galaxies lies a profound emptiness. These cosmic voids are not just empty space. They are the largest structures in our universe, immense regions spanning hundreds of millions of light years. And within their vast nothingness, they hold the key to a hidden symmetry that orchestrates everything we see. By the end of this, you will understand how these great nothings are actively shaping the cosmos and rewriting the rules of physics. We will uncover what these voids reveal about the invisible force tearing the universe apart, and how the birth of emptiness might be connected to the birth of everything. What does true emptiness make you wonder about our place in the universe? The cosmos is structured like a vast, intricate spiderweb. Galaxies are not scattered randomly. They cluster into brilliant filaments and immense walls, tracing patterns across the darkness. And between these glittering structures lie the voids, colossal bubbles of near-nothingness. These cosmic voids are the dominant feature of our universe, each one an underdense desert spanning hundreds of millions of light years. They are not perfect vacuums, but regions of exceptionally low density where you might find only a handful of isolated galaxies, adrift in an ocean of emptiness. Astronomer Rien van der Weygaert poetically calls them the universe's deserts, places where the normal rules seem to bend. Within these voids, gravity's pull is weaker, and the push of dark energy is stronger, making them critical laboratories for studying cosmic evolution. Their defining characteristics are their sheer scale, their sparse matter content, and their role as perfect counterpoints to the dense, bustling galaxy clusters. To understand a void is to recognize it as a dynamic environment, not a static whole. It is a place where subtle physics manifests on a grand stage, where the faint whispers of cosmic forces become audible. This foundational knowledge primes us to see these great emptinesses not as absences, but as cosmic mirrors, reflecting a hidden symmetry that governs all of existence. This cosmic sponge structure, with its vast hollow gaps, is known as the cosmic web. It is the grand architecture of the universe, a pattern first revealed by painstakingly mapping the positions of millions of galaxies. In this sprawling web, the brilliant clusters and filaments are the solid material, but the voids are the hollows, the empty spaces that give the structure its form. And just as the silence between musical notes defines the rhythm and melody of a song, these voids are the negative space that gives meaning to the universe's positive structures. They are not an afterthought. Voids occupy the overwhelming majority of cosmic volume. Their existence and arrangement are fundamental to the universe's design. This web did not appear by chance. As cosmologist J. Richard Gott III described, it is the final result of minuscule fluctuations in the dense, hot soup of the Big Bang. Imagine the faintest ripples in a primordial sea, so small they were almost nothing. Over billions of years, gravity acted as an amplifier. It pulled matter toward those slightly denser ripples, leaving the less dense areas to steadily empty out. This is the process of gravitational repulsion. Matter does not just flow toward the dense clusters, it actively flows out of the underdense regions, evacuating them and creating these expanding bubbles of emptiness. The placement of these voids is not chaotic. Look closely and you see a hierarchy, a pattern within the pattern. Smaller voids nestle neatly inside larger ones, like bubbles within bubbles, all arranged in a vast, interconnected network. This intricate, layered architecture is not random. It points toward a deep and underlying order, a profound symmetry in the very fabric of space, where the distribution of matter and emptiness is perfectly, mysteriously balanced. For centuries, astronomers pictured a universe where galaxies were sprinkled evenly, like dust across a floor. This comforting uniformity was shattered in the 1970s and 80s. Pioneers like Stephen Gregory and Laird A. Thompson were meticulously mapping galaxy positions, creating the first three-dimensional charts of the cosmos. What they found was not a smooth distribution, but a startling pattern of immense dark gaps. The most famous of these, the Boötes Void, was a staggering discovery. A spherical region of space over 300 million light-years wide, containing almost nothing. It was a hole in the universe so vast you could fit thousands of galaxies inside, yet it held only a handful. The legendary physicist Vera Rubin captured the feeling perfectly, comparing it to the moment early explorers discovered new continents. Our cosmic map was suddenly redrawn, revealing a world of structure and emptiness we never knew existed. This revelation was driven by technology. Early redshift surveys, which measured the light from galaxies to determine their distance, slowly pieced together the true scale of the cosmos. Later, monumental projects like the Sloan Digital Sky Survey provided a flood of data, turning faint points of light into a detailed blueprint of the cosmic web. The initial skepticism from the scientific community was understandable. Finding such a colossal void seemed to defy the laws of probability and our basic assumptions about the cosmos. But as more and more empty regions were catalogued, the evidence became undeniable. Voids were not flukes or errors in the data. They were fundamental, essential features of the universe's architecture. This historical shift was profound. It forced cosmologists to abandon the simple model of a uniform cosmos and embrace a new, lumpy reality, one where the empty spaces were just as important as the bright clusters. This necessary revision of our cosmic models was the essential first step, the moment we cleared the board, preparing it for the discovery of a deeper, hidden symmetry waiting to be uncovered. This dominance of emptiness creates a perfect stage for the universe's most mysterious actor, dark energy. Inside a cosmic void, gravity's pull is exceptionally weak. With so little matter to create a counterforce, the repulsive push of dark energy is amplified. Think of a void as a balloon expanding in a room where the air pressure is steadily increasing. The balloon's thin, elastic skin stretches more easily than the dense walls around it. In the same way, the emptiness of a void allows it to respond more freely and dramatically to the underlying push of dark energy that permeates all of space. As cosmologist Laura Mersini-Horton suggests, these regions act as cosmic magnifying glasses, making the subtle effects of this force impossible to ignore. This gives astronomers a powerful probe. By measuring how quickly these voids grow over cosmic time, they can take the temperature of dark energy itself. The key measurement is the Hubble constant, which describes the rate of the universe's expansion. But by comparing the expansion rate of the empty voids to the more sluggish expansion of the dense galaxy clusters, scientists can deduce the properties of what is driving it all. Is dark energy a constant force, an unchanging property of space itself, as Albert Einstein once proposed, or is it something dynamic, a force that has evolved and changed in strength over billions of years? The growth rate of these cosmic bubbles holds the answer. A void that expands at one rate points to a static dark energy. A void that expands at a different rate reveals an evolving one. Each observation, each precise measurement of a void's boundaries, helps narrow down the possibilities, bringing us closer to understanding the fundamental symmetry between the universe's large-scale structure and the invisible energy that is tearing it apart. These cosmic laboratories of emptiness offer a unique space to test the very laws of gravity. Inside a void, the rules of Einstein's general relativity operate in a purer form, stripped of the chaotic interference found in crowded galaxy clusters. Imagine trying to hear a single, quiet instrument in a silent concert hall versus a roaring stadium. The void is that silent hall where the subtle notes of spacetime geometry can be heard with perfect clarity. Physicist Timothy Clifton points out that this simplicity is their greatest strength. The weak and uniform gravitational field within a void reduces confounding factors, creating a clean test bed for the fundamental predictions of relativity. Scientists perform these tests by watching how galaxies move on the edges of these empty regions. These are not the grand, sweeping motions of cosmic expansion, but smaller, more peculiar velocities, the subtle shifts as galaxies are gently tugged by the void's gravitational influence. Another crucial test comes from gravitational lensing. In a dense cluster, gravity bends light from distant objects, creating dramatic arcs and rings. In a void, the effect is far more subtle, a faint warping of the cosmic background radiation as it passes through these underdense regions. This faint signature reveals how the void's gravity, or lack thereof, distorts the fabric of spacetime itself. If general relativity holds perfectly true, the expansion and gravitational pull of these voids will match precise mathematical predictions. But if we see an anomaly, if a void grows a little too fast or its lensing effect is a little too weak, it could be the first crack in a foundational theory, a sign that our understanding of gravity itself needs revision. This makes every void a guardian of cosmic symmetry, a place where the elegant balance of Einstein's universe is either confirmed or called into question, hinting at principles even deeper than those we currently know. The oldest light in the universe carries the scars of these great emptinesses. This is the cosmic microwave background, the faint afterglow of the Big Bang that fills every corner of space. As this ancient light travels for billions of years to reach our telescopes, its journey is not undisturbed. When a CMB photon enters a cosmic void, it begins a slow, arduous climb out of a gravitational well. But this well is a strange one, defined more by what is absent than what is present. Because the void has so little matter, its gravitational pull is weak, acting like a shallow hill rather than a deep valley. As the photon climbs out, it must expend energy, but the hill is not as steep as it was when the photon first entered, because the void has been expanding and becoming even emptier due to dark energy. This imbalance means the photon loses more energy climbing out than it gained falling in, and this energy loss manifests as a tiny, specific dip in its temperature. We see this as a cold spot in the cosmic microwave background, a subtle shadow cast by a void hundreds of millions of light years away. This phenomenon is known as the integrated Sachs-Wolfe effect, a direct imprint of cosmic structures on the most primordial light. Nobel laureate George Smoot described mapping these imprints as reading the universe's fingerprint, where the voids leave their unique signature for us to decode. Satellites like Planck have scanned the entire sky, creating exquisitely detailed maps of the CMB's temperature variations. When scientists overlay these maps with charts of known cosmic voids, the correlation is startling. Cold spots on the CMB frequently align perfectly with the locations of these vast empty regions. This is not a coincidence. It is a direct measurement of dark energy at work. The fact that the photon loses that extra bit of energy is proof that the gravitational landscape of the void is changing during the photon's journey, and the only force that can cause that change on such a scale is the repulsive push of dark energy. This creates a profound symmetry, a direct link between the universe's first light and its ultimate fate. The pattern of cold spots we see today is a fossil record, a bridge connecting the microscopic ripples of the Big Bang to the grand, empty architecture of the modern cosmic web. It reveals a universe where light and emptiness are in constant, silent conversation, telling a story that began at the dawn of time. The very seeds of these cosmic voids were planted in the first fraction of a second of the universe's existence. During a period called inflation, the cosmos underwent a burst of expansion so rapid it was faster than the speed of light. In this furious stretching of spacetime, the tiniest quantum jitters, fluctuations that were mere wrinkles in the fabric of reality, were blown up to cosmic proportions. These magnified ripples became the primordial blueprint for all future structure, the subtle hills and valleys in the density of the universe. The denser hills would eventually collapse under gravity to form the great clusters and filaments of galaxies. But the valleys, the regions of slightly lower density, were destined to become the cosmic voids. This reveals a profound and hidden symmetry. The brilliant web of galaxies and the vast deserts of emptiness are not opposites. They are two sides of the same coin, born from the same set of initial conditions, one the positive imprint and the other the negative. Cosmologist Alan Gough's theory of inflation makes a very specific prediction about these initial ripples. It says they should be nearly scale invariant. What does that mean in plain terms? It means the universe should have started with ripples of all sizes, from the very small to the unimaginably large. And this is exactly what we observe when we look at the void network today. We see a hierarchy of emptiness with small voids nestled inside medium ones, which are in turn contained within the largest supervoids spanning hundreds of millions of light years. This nested, bubble-like structure is a direct echo of the inflationary epoch. The statistical properties of these voids, their size distribution and their shapes, serve as a rigorous test for the models of our universe's birth. By counting voids of different sizes, scientists can measure a key inflationary parameter called the spectral index. This number tells us precisely how the strength of those initial ripples varied with their size. If the pattern of voids matches the prediction of a nearly flat spectral index, it powerfully confirms the inflationary paradigm. But the implications run even deeper into realms that sound like science fiction. Some models of eternal inflation suggest our universe is just one bubble in a vast, ever-expanding multiverse. If this is true, the properties of our largest cosmic voids might carry a faint signature of that greater cosmic foam. Could the shape of a particular supervoid or an unexpected statistical distribution be evidence that our universe once collided with another bubble in the multiverse? While this remains a speculative frontier, it highlights the incredible power of these empty regions. They are not passive absences, they are active fossils preserving information from the universe's first moments. By studying the Great Nothing, we are indirectly probing the instant of creation, uncovering a symmetry so fundamental it connects the birth of everything to the architecture of emptiness we see today. This silent network is a living relic, a direct line back to the inflationary bang, waiting to tell us how it all began. Supercomputers allow us to rewind the tape of the universe and watch these voids be born. Inside these vast digital laboratories, cosmologists program the laws of physics and the initial conditions from the Big Bang, then set a virtual cosmos in motion. The simulation begins with a nearly smooth distribution of dark matter and gas, seeded with the faintest ripples. As the clock starts ticking, gravity begins its relentless work. You can watch it happen in accelerated time. Matter starts to drain away from the broad, shallow valleys flowing toward the sharper peaks. The underdense regions do not just sit there. They actively evacuate, their boundaries sharpening as more and more material is pulled out by the gravitational attraction of the surrounding filaments and clusters. This process, known as gravitational instability, is the engine that carves the cosmic web. Landmark simulations like the Millennium Run have shown this evolution in stunning detail, tracing the journey from a homogeneous soup to a spongy network over billions of virtual years. Researcher Mark Nairink emphasizes the power of this approach, noting that we can literally watch voids grow, tracking their expansion and merger history in a way real-time observation never could. This virtual experimentation provides a crucial testing ground. Scientists can tweak the fundamental parameters, altering the amount of dark matter or the strength of dark energy, and then observe how the simulated void network responds. The shapes of these digital voids are particularly revealing. They are not random. In a universe dominated by dark matter and dark energy, voids tend to become more spherical as they evolve. Their walls are squeezed by the collapse of surrounding structures, pushing them into rounder, more pressurized bubbles. If the properties of dark energy were different, however, the voids might stretch into long, ellipsoidal sausages or collapse in on themselves entirely. This is where the symmetry between theory and observation becomes concrete. Astronomers take the statistical properties of voids from these simulations, their sizes, shapes, and distribution, and compare them directly to the map of the real cosmos from galaxy surveys. When the virtual voids match the real ones, it is a powerful confirmation that our model of the universe is on the right track. It is a perfect feedback loop where the great emptinesses of the real world guide the construction of their digital counterparts, and those digital twins, in turn, reveal the hidden forces shaping our reality. Deep within these cosmic deserts, a few solitary galaxies drift in profound isolation. These are the void galaxies, the hermits of the cosmos, evolving in a quiet environment so different from the bustling galactic cities of the clusters. One of the most famous examples is a spiral galaxy known as MCG plus 01020015, often called the loneliest galaxy in the universe. It resides in a region of space so empty that its nearest galactic neighbor is over 1 million light-years away. This extreme isolation has profound consequences. Freed from the gravitational harassment and violent collisions that are commonplace in crowded galactic clusters, these void dwellers represent a purer, more undisturbed form of galactic evolution. As astronomer R. Brent Tully observed, they tend to be bluer, younger, and more irregular in shape. Their bluer color is a direct sign of vigorous star formation, a fire that continues to burn brightly because it has never been extinguished by a disruptive encounter with another galaxy. In the dense urban centers of galaxy clusters, such interactions are frequent, often stripping galaxies of their gas, the raw material for new stars, and leaving them as red and dead ellipticals. But in the void, a galaxy can hold onto its gas for billions of years. This leads to another key difference: their metal content. In astronomy, any element heavier than hydrogen or helium is considered a metal. These elements are forged in the hearts of stars and scattered through space by supernova explosions. In a crowded cluster, this processed material is constantly recycled, enriching the gas that will form the next generation of stars. In a void with so few neighbors, this enrichment process happens more slowly. The gas remains pristine, and the stars that form from it are consequently more metal-poor. This also affects their dark matter halos. The tranquil environment of a void means these halos are less disturbed, potentially growing in a more symmetrical and predictable way compared to the twisted and stripped halos found in clusters. Studying these galactic outliers is like running a controlled experiment on a cosmic scale. It allows astronomers to disentangle nature from nurture in galaxy development. Is a galaxy's fate determined solely by its initial conditions, its nature, or is it shaped by its environment, its nurture? By comparing a void galaxy to its cluster counterpart, we see that both are true. The same universal laws of physics are at work, but they produce dramatically different outcomes based on local conditions. This reveals a beautiful symmetry in diversity, a demonstration that the cosmos expresses its creative potential in countless ways, from the crowded metropolises to the silent, star-forming hermits of the great emptiness. Even in the deepest cosmic void, the universe is never truly empty. It is filled with an invisible presence, dark matter, whose subtle gravitational pull helps sculpt the void's very boundaries. While these regions are deserts of visible matter, they are still permeated by this mysterious substance, offering a uniquely clean laboratory to study it. In the crowded, chaotic environment of a galaxy cluster, the gravitational effects of dark matter are tangled with the violent interactions of stars and gas. But inside a void, the signal is pure. With so little ordinary matter to mask the subtle pull, the true nature of dark matter becomes clearer. Physicist Lisa Randall points out that these quiet expanses could reveal if dark matter particles interact with each other in ways we have not yet detected. In a dense cluster, such subtle self-interactions would be lost in the noise, but in the low-density environment of a void, even a faint whisper of particles colliding or scattering would stand out, amplifying signals that are otherwise impossible to hear. Scientists map this invisible scaffold using a technique called weak gravitational lensing. They observe how the light from distant galaxies is ever so slightly distorted as it passes by the edges of a void. This distortion is a footprint, a direct measure of the total mass, both seen and unseen, contained within that region of space. The resulting map shows the dark matter density profile, the precise way the concentration of this invisible substance changes from the void's empty center to its denser outer walls. These observed profiles are then compared to high-resolution computer simulations based on our standard model of cosmology, known as lambda CDM. In this model, dark matter is cold and collisionless, moving slowly and interacting only through gravity. The simulations predict a specific, gentle slope for the dark matter distribution within a void. When the real-world data matches this prediction, it is a powerful confirmation of our fundamental theories. But what if it does not match? A discrepancy could be the first sign of new physics. If the dark matter in a void appears more spread out or clumped differently than expected, it might suggest that dark matter is not completely cold and slow. It could instead be warm, made of faster-moving particles that resist collapsing into the sharp structures predicted by the standard model. Alternatively, the gravitational effects we see might not be from dark matter at all, but a sign that our understanding of gravity itself, Einstein's general relativity, needs to be modified on the largest scales. Each void becomes a natural detector, a cosmic instrument probing the symmetry between the seen and the unseen. By studying the great nothing, we are not just looking at an absence. We are measuring the presence and behavior of the universe's dominant, yet most elusive component, using emptiness itself to illuminate the dark. This nested architecture of emptiness reveals a universe built like a set of cosmic Russian dolls. Small voids reside comfortably inside larger ones, which themselves are contained within even more immense supervoids, creating a hierarchy that spans from scales of a few million light-years to structures over 1 billion light-years across. This is not a chaotic jumble, but a fractal-like pattern where the same basic shape of emptiness repeats itself at different magnifications. A small void and a giant supervoid are essentially cousins, born from the same physical process but at different scales. This self-similarity is the hallmark of a deep, scale-invariant symmetry woven into the fabric of the cosmos. It means the rules that govern the formation of a relatively small void, just tens of millions of light-years wide, are the very same rules that orchestrate the birth of a colossus spanning hundreds of millions of light-years. Cosmologist Francesco Sillo's Labini has meticulously analyzed this pattern, showing that the number of voids of a given size follows a precise mathematical relationship known as a power law. Double the size of the void you are looking for, and you will find roughly a quarter as many of them. This is not a random distribution. It is the same kind of statistical fingerprint seen in other complex, evolving systems, from the branching of trees to the swirls of turbulent fluids. The universe, in its grand design, seems to favor certain patterns of organization, whether it is arranging matter or defining emptiness. The evidence for this hierarchical order is written across the sky in the data from massive galaxy surveys like the 2-degree field and the Sloan Digital Sky Survey. These projects have mapped the positions of millions of galaxies, and when you filter out the bright clusters and filaments, the void network emerges with stunning clarity. You can see tiny underdensities peppering the walls of larger voids, and those larger voids sometimes sharing a common boundary or even merging over cosmic time. This interconnected web of nothingness tells a compelling story. It implies that the physical processes that sculpt the cosmos, from the initial tug of gravity to the persistent push of dark energy, are universal. They operate with the same fundamental principles whether they are working on a relatively local patch of space or on a volume encompassing a significant fraction of the observable universe. Recognizing this ordered hierarchy in what appears to be mere absence is a profound shift in perspective. It points to a cosmos where emptiness is not a flaw or a vacancy, but an essential, structured component of a beautifully symmetrical design. These frozen sound waves from the primordial universe create a perfect cosmic yardstick. Known as Baryon acoustic oscillations, these are the fossilized imprints of pressure waves that race through the hot, dense plasma of the early cosmos. Think of the universe moments after the Big Bang as a vast, seething pond. A single, tremendous event, like a stone dropping into the water, sent powerful ripples expanding outward. In the cosmic case, that stone was the initial density fluctuation, and those ripples were waves of compressed matter and radiation. For hundreds of thousands of years, these waves expanded at nearly half the speed of light, until the universe cooled enough for atoms to form, freezing the waves in place. This process imprinted a preferred scale onto the cosmos, a specific distance that became the most common separation between cosmic structures. It is like finding that all the pebbles on a beach are consistently spaced exactly 1 foot apart. This is the standard ruler that astronomer Daniel Eisenstein so aptly named. Now, here is where the voids become essential. When we look at the map of the cosmic web, we find that the boundaries of these vast empty regions, their outer shells, align remarkably well with the peaks of these ancient acoustic waves. Because voids are so clean and underdense, their edges are sharply defined against the surrounding filaments, making this acoustic signal incredibly clear and easy to measure. It is like trying to hear a specific musical note in a quiet room versus a noisy city street. The void is the quiet room, where the pure tone of that primordial sound wave rings out without interference. Major astronomical surveys like the Dark Energy Spectroscopic Instrument, DAISY, and the Euclid Space Telescope are now using this principle with breathtaking precision. They map the three-dimensional positions of millions of galaxies, and just as importantly, the voids between them. By measuring the typical size of these voids and comparing it to the known length of the Baryon acoustic oscillation ruler, scientists can determine how much the universe has stretched since that sound wave was frozen in time. This provides an exquisitely accurate measurement of cosmic distances across billions of years, which directly translates into a precise value for the Hubble constant and the properties of dark energy. The profound symmetry revealed here is breathtaking. The same preferred scale, the same cosmic rhythm, is found etched into both the densest clusters of galaxies and the emptiest voids. This uniform pattern tells us that the initial conditions of our universe were remarkably consistent and symmetric, a single set of physical laws orchestrating both the something and the nothing. The great emptiness does not break the cosmic pattern. It completes it, offering the clearest view we have of the universe's fundamental geometric balance. But our universe might not be the only possible one. The behavior of these cosmic voids could reveal a cosmos governed by entirely different rules. In alternative theories of gravity and dark energy, the great emptinesses would not behave as we expect. Imagine a theory like modified Newtonian dynamics or MUND, which proposes that gravity works differently at very low accelerations, eliminating the need for dark matter. In such a cosmos, the weak gravitational fields inside voids would be the ultimate testing ground. Without dark matter to provide a stabilizing scaffold, these voids might expand at wildly different rates, or their shapes could distort into long, filamentary tunnels instead of rounded bubbles. Another compelling alternative involves a dynamic form of dark energy known as quintessence, a cosmic fluid that changes its repulsive strength over time. In a quintessence-dominated universe, voids would act as powerful amplifiers for this evolving force, potentially expanding far more rapidly than in our standard model. Physicist Stacy McGaw has long argued that these low-density environments are where deviations from standard physics become impossible to ignore. They strip away the complex noise, leaving only the pure signal of the underlying forces. The testable predictions of these models lie in the subtle statistics of the void network. In our standard lambda CDM model, voids have a specific range of sizes and a gently sloping density profile from their empty centers to their dense walls. But in a modified gravity theory like F of R gravity, the extra repulsive force generated by the curvature of space itself could make voids larger, emptier, and more numerous. Their radial profiles might show a sharper drop in density, a stark cliff instead of a soft hill. Scientists are now comparing these theoretical predictions with a flood of new data from observatories. If we find a population of voids that are too spherical, or a void that is expanding significantly faster than our models allow, it would be a crack in the foundation of modern cosmology. Such an anomaly would not just be a curious detail, it would be a beacon pointing toward a deeper, more complex reality where the symmetry we perceive is merely a shadow of a truer, more profound order. The silent voids are therefore the ultimate arbiters, holding the power to confirm our most cherished theories or to shatter them, forcing us to rewrite the fundamental laws of the cosmos. Mapping the great emptiness begins with an immense cosmic census. Astronomers do not simply point a telescope at a dark patch of sky and declare it a void. The process is a sophisticated digital excavation, peeling back layers of the universe in 3 dimensions to reveal the hollows within. The primary tool for this is the Galaxy Redshift Survey. By capturing the light from millions of galaxies, astronomers can measure their redshift, a stretching of light waves caused by the expansion of the universe. This redshift acts as a cosmic tape measure, telling us not only how far away each galaxy is, but also how the space between them has stretched over billions of years. When you plot the 3-dimensional positions of all these galaxies, the cosmic web emerges, and the vast, underdense regions become starkly apparent. But how do you precisely define the edge of nothing? This is where advanced algorithms come into play. One of the most powerful is the watershed transform. Imagine pouring virtual water over the three-dimensional map of the cosmos. The water naturally collects in the lowest points, which are the densest galaxy clusters. The watershed lines, the ridges where the water from different basins would meet, define the boundaries of the voids. It is a mathematical way of finding the natural contours of emptiness. Through massive projects like the Sloan Digital Sky Survey, these techniques have catalogued thousands of these cosmic bubbles, each with its own unique size, shape, and location in the grand architecture. This statistical mapping must account for a crucial bias. Galaxies are not perfect tracers of the underlying mass. Bright, massive galaxies are easier to see, but they only form in the densest peaks of the cosmic web. To truly understand a void, scientists must statistically correct for these observational limitations, inferring the true distribution of all matter, both seen and unseen. As researcher Alice Dupuy explains, this is where machine learning is revolutionizing the field. New algorithms can be trained on colossal computer simulations of the universe, learning to recognize the subtle signature of a void in the complex, noisy data of a real galaxy survey. This allows for a more accurate and automated creation of void catalogs from ever larger datasets, turning a painstaking manual process into a powerful, scalable discovery engine. Several key techniques form the backbone of this search. Nearest neighbor searches calculate the average distance from one galaxy to its closest companions, instantly highlighting regions where those distances become extraordinarily large. Density field reconstructions take the discrete points of light from galaxies and smooth them into a continuous 3D map of matter density, revealing the vast low-density basins as clearly as topographic maps show valleys. For looking into the deepest, earliest reaches of the universe, astronomers use photometric data. This method uses the brightness of a galaxy through different color filters to estimate its redshift, a less precise but far faster technique that allows surveys to map immense volumes of space. These consistent methods are vital. They ensure that a void discovered in one survey is defined the same way as a void in another, allowing for apples-to-apples comparisons across the cosmos. This rigorous technical foundation, this precise cartography of nothing, is what enables the breathtaking measurements of dark energy and cosmic symmetry, transforming empty space into our most revealing cosmic laboratory. The relentless expansion of these cosmic voids is quietly writing the final chapter of our universe. As dark energy's repulsive push grows stronger over billions of years, these empty regions will not just grow, they will begin to merge. Smaller voids will coalesce into larger ones, swallowing the thinning filaments that once connected the cosmic web. Galaxies, even those in the great clusters, will find themselves increasingly isolated, their brilliant cities fading into islands adrift in an ever-growing ocean of darkness. This is the trajectory toward the Big Freeze, a cold, dark cosmos where the last stars flicker out and the universe approaches a state of maximum entropy, a profound and permanent equilibrium. Cosmologist Katie Mack describes this not as a dramatic explosion, but as a slow, inexorable fading, where the dynamics of these voids are the central actors in the final act. Their accelerating growth is the engine of cosmic dissolution. The ultimate fate, however, hinges on the precise nature of dark energy. If dark energy remains a constant force, as in our standard model, the outcome is this gradual heat death. But if dark energy is something more volatile, like a field called quintessence that grows stronger over time, the end could be far more dramatic. In a scenario known as the Big Rip, the repulsive force could become so powerful that it overwhelms all binding forces, not just expanding the voids but tearing apart galaxies, solar systems, and even atoms themselves in a final, catastrophic moment. The voids would be the first to feel this ferocious expansion, their boundaries stretching at an unimaginable rate until they are all that remains. This progression reveals a profound and poetic symmetry. The same process of gravitational instability that carved the cosmic web from a smooth primordial soup, pulling matter into clusters and evacuating the voids, is now being reversed by dark energy. The universe is, in a sense, unraveling. The intricate architecture forged over billions of years is being systematically taken apart, returning to a state of homogeneity, but this time a cold, empty one instead of a hot, dense one. It is a cosmic bookend where the initial conditions of structure and the final state of dissolution are two sides of the same symmetrical equation. To understand the voids of today is to hold a window to the very end of time, seeing how the great emptiness that began as a tiny ripple will one day become the entire story. There is a profound beauty in these great voids, a stark aesthetic that transcends their scientific definition. We often think of the cosmos as a spectacle of brilliant lights, but the emptiness holds its own powerful allure. The vast, simple geometry of a void, a sphere of near-nothingness spanning hundreds of millions of light-years, brings a sense of order and peace to the universe's chaotic web. It is the visual silence between the notes, an essential element of the cosmic composition. Artists who work with astronomical data, like photographer Michael Benson, understand this intuitively. They translate the raw information from galaxy surveys into breathtaking imagery, where the voids are not blank spaces but active participants. In these visualizations, the great emptinesses are rendered as deep, resonant backgrounds of black and indigo, against which the fiery filaments of galaxies gleam all the more brightly. This artistic representation captures a fundamental truth about the cosmos, the perfect balance between fullness and void. This aesthetic resonates deeply with principles found in Japanese philosophy, specifically the concept of wabi-sabi, which finds beauty in imperfection, impermanence, and importantly, in emptiness. In a wabi-sabi view, an empty space in a room is not a lack to be filled, but a vital element that gives the occupied spaces their meaning and breadth. A cosmic void is the ultimate expression of this, a vast and imperfect emptiness that is essential to the universe's asymmetric symmetry. This artistic and philosophical lens is not new. For centuries, Tibetan monks have created intricate mandalas, only to destroy them in a ritual that honors impermanence and the void from which all form emerges. Modern installation artists build works that explore the power of negative space, using absence to define presence. When we look at a cosmic void through this dual lens, its impact is transformative. The symmetry it reveals is not just a mathematical equation in a physics textbook. It is a perceptual symmetry, a balance that we can feel. It speaks to a deep, human appreciation for the harmony between something and nothing, between the intricate and the simple. This artistic dimension enriches our scientific quest, reminding us that the universe's hidden order is not just something to be calculated, but also to be contemplated. The great voids in their silent, majestic emptiness are perhaps the universe's most profound work of art. These cosmic voids might be more than just empty pockets in our own universe. They could be scars from a much grander reality, imprints left by universes that exist beyond our own. Picture our entire cosmos not as the entirety of existence, but as a single bubble floating in an infinite, frothing sea of other bubble universes, a multiverse. In this breathtaking scenario, the vast emptiness of a cosmic void could be the lingering echo of a long-ago collision with another cosmic bubble. When such bubbles meet, their boundaries could create regions of space with fundamentally different properties, areas where the laws of physics or the values of nature's constants are subtly altered. These regions would appear to us as voids, immense deserts where the normal rules of our universe seem to break down. The theoretical physicist Alexander Vilenkin explores this possibility, suggesting that the boundaries between colliding bubbles could leave observable signatures. We might detect these imprints as strange, anomalous patterns in the cosmic microwave background radiation, or as unexplained density profiles within the largest supervoids. The voids themselves could act as natural telescopes, not for seeing distant galaxies, but for glimpsing the physics of a neighboring cosmos. This idea pushes speculation to its limits, proposing that some voids could be weak spots in the fabric of our reality, portals of a sort where the influence of another universe subtly leaks through. While these concepts are highly theoretical and sit at the very frontier of cosmology, they fundamentally reshape our understanding of cosmic symmetry. The hidden symmetry voids reveal may not be confined to our universe alone. It could be a fragment of a much vaster, multiversal order, a pattern that repeats across an infinity of cosmic bubbles. The great emptinesses we map could be our first, faint clues that our universe is just one note in a far grander symphony. These silent voids become highways for the universe's most energetic particles. High-energy cosmic rays, primarily protons and atomic nuclei traveling at nearly the speed of light, race across the cosmos. When one of these particles enters a void, its journey changes dramatically. The near absence of matter means there are far fewer atoms to collide with, allowing the particle to travel vastly greater distances without being scattered or absorbed. More importantly, the magnetic fields within these regions are exceptionally weak. Since magnetic fields bend the paths of charged particles, a weak field means a straighter path. A cosmic ray passing through a crowded galaxy cluster would be whipped around like a leaf in a hurricane, its original direction completely lost. But inside a void, it travels as if on a freshly paved, empty freeway, its trajectory remaining remarkably straight. This unimpeded travel transforms these great emptinesses into perfect conduits, offering a clear line of sight back to the particle's origin. The mystery of ultra-high-energy cosmic rays has puzzled scientists for decades. These are the most energetic particles ever observed, each carrying the punch of a professionally thrown baseball, but compressed into a single subatomic particle. Where do such tremendous energies come from? The prime suspects are cataclysmic events like active galactic nuclei, where supermassive black holes unleash colossal jets of energy, or perhaps supernova in their most extreme forms. Yet when these particles arrive at Earth, their paths are often scrambled by the magnetic fields they have traversed, obscuring their birthplace. This is where void maps become an essential tool. By correlating the arrival direction of an ultra-high-energy cosmic ray with the known locations of cosmic voids, astronomers can perform a kind of cosmic triangulation. If a particle's path seems to have passed cleanly through a long, clear void, it dramatically narrows down the potential sources to those that lie on the far side of that emptiness. Astrophysicist Glenys Farrar's work highlights how this process provides a dual insight. It not only helps pinpoint the accelerators of these particles, but also reveals the strength and structure of the faint intergalactic magnetic fields that the particle barely encountered. The symmetry at play is one of uniform conditions. The void acts as a standardized laboratory, offering the same clean, low-noise environment for any particle passing through it. This consistency allows scientists to compare signals and isolate variables in a way that is impossible in the messy, magnetized environments of galaxy clusters. Observatories like the Pierre Auger Observatory in Argentina are putting this method into practice. Its vast array of detectors records the showers of particles created when a cosmic ray strikes the atmosphere. By combining this arrival data with three-dimensional maps of the cosmic web, researchers can trace back the likely path of the particle, using the voids as guiding tunnels through the cosmic clutter. Each high-energy event that can be linked to a void corridor brings us closer to solving a fundamental mystery, revealing how the great emptinesses not only shape the structure of space, but also guide the very particles that journey through it. This philosophical nothingness is not a sterile emptiness, but a vibrant, seething arena. Our most powerful theories in cosmology and quantum physics converge to tell us that a true vacuum, a state of absolute nothing, does not exist. Even in the deepest cosmic void, space is not truly empty. It is filled with the persistent hum of quantum fields, a faint energy that permeates every cubic centimeter of the universe. Think of it as the universe's lowest possible energy setting, a baseline activity that never shuts off. Within this quantum vacuum, pairs of virtual particles flicker in and out of existence, borrowing energy from the fabric of space itself for unimaginably brief moments before annihilating each other. This is not just theoretical speculation. We see its effects in lab experiments like the Casimir effect, where two metal plates placed extremely close together in a vacuum are gently pushed together by the pressure of these virtual particles popping into being outside the plates. The philosopher Jean-Paul Sartre grappled with the concept of nothingness as a force that defines being, and in a strange way, the cosmic void embodies this. It is the backdrop against which existence is defined, yet it is itself a dynamic something. Cosmologist Lawrence Krauss has extensively explored this idea, arguing that what we call nothing is in fact a rich and complex physical state, brimming with potential. This redefinition is crucial. When we say a cosmic void is empty, we mean it is empty of stars and visible galaxies, but it is full of the invisible machinery that may be driving the cosmos. The dark energy that accelerates the universe's expansion is thought to be a property of this vacuum energy. The quantum fluctuations within these vast emptinesses might be the very source of this repulsive force. This creates a profound link between the unimaginably small world of quantum mechanics and the grandest scales of the cosmic web. The same tiny jitters that seeded galaxies also fill the voids with a latent energy that now dictates their growth. Here lies a breathtaking symmetry. The something of the cosmic web and the nothing of the voids are not opposites. They are partners in a cosmic dance, both emerging from the same underlying quantum reality. The void is not a passive absence. It is an active participant, its inherent energy shaping the destiny of all that is. To peer into a void is to gaze upon the fundamental canvas of reality, where the distinction between something and nothing blurs into a single, unified whole. This sprawling network of cosmic bubbles is now becoming a precision instrument. We are learning to use the voids themselves as a new kind of cosmic calibrator, a tool to measure the fundamental numbers that define our universe. Just as astronomers use standard candles like supernova to gauge distances, they are now using the statistical properties of voids to measure parameters like the overall matter density of the cosmos and the rate of its expansion. The sheer abundance of voids, their distribution of sizes, and even their shapes are not random. They are a direct output of the universe's recipe, a reflection of the exact amounts of dark matter, dark energy, and ordinary matter that were stirred into the cosmic mix. Because these voids form through the clean, well-understood process of gravitational collapse and evacuation, their statistics provide a powerful and independent check on other methods. This is crucial for rooting out hidden systematic errors that might subtly bias measurements from supernova or the cosmic microwave background. Physicist Nico Hamhaus has pioneered sophisticated models that treat the clustering of voids the way they themselves are distributed in space as a sensitive probe. The subtle tendency for voids to avoid each other, creating a specific pattern in their positions, carries an imprint of the gravitational forces that shaped them. This void clustering can now achieve a competitive accuracy with established techniques, offering a completely different path to the same answers. The real power emerges when we combine these paths. Massive void catalogs from surveys like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time are fed into complex likelihood analyzers. These are statistical engines that test millions of possible universes, each with different values for key numbers like omega m, the total matter density, or sigma 8, which measures the clumpiness of that matter. The computer asks which of these simulated universes produces a void population that looks exactly like the one we see in the real sky. The answer pins down these cosmological parameters with remarkable precision. When the void-based measurement for the Hubble constant agrees with the value from the cosmic microwave background or from distant supernova, it is not just a mere confirmation. It is a profound reinforcement of a symmetric reliability. It tells us that our model of the cosmos is coherent, that the same laws of physics deduced from the ancient afterglow of the Big Bang also govern the evolution of the largest structures in the modern universe. This calibrating role, using the great emptiness to measure the fullness of cosmic reality, makes voids an indispensable tool in our final quest for a truly precise understanding of everything. The voids we observe today were not always these immense, empty bubbles. To find their origins, we must journey back to the universe's youth, to a time when the cosmos was a far more crowded and uniform place. In these early epochs, voids were smaller, shallower regions, not the starkly defined deserts of the modern universe. They were subtle dimples in the density of the cosmos, regions that were only slightly less crowded than their surroundings. The matter within them was still relatively dense, and their boundaries were fuzzy and ill-defined. It was the relentless work of gravity over billions of years that carved them into their current form. Gravity acted as a cosmic sculptor, pulling matter out of these underdense valleys and depositing it into the growing hills that would become galaxy clusters and filaments. As matter steadily drained away, the voids began to empty out, their interiors becoming ever more rarefied while their boundaries sharpened into the distinct walls we map today. This evacuation was not a gentle process, but a dynamic and accelerating one. Astronomer Julian Dalcanton emphasizes that by observing voids at different redshifts, which correspond to different look-back times in cosmic history, we can watch this entire movie play out in reverse. We see the universe's structure gradually simplifying, the voids becoming less empty and more blended with the web as we peer further back in time. This temporal perspective is crucial because the rate at which a void grows and empties is a direct record of the forces acting upon it. The gravitational pull from the surrounding matter works to slow a void's expansion, while the push of dark energy works to accelerate it. By measuring the growth rate of voids across cosmic time, we get a direct readout of this cosmic tug-of-war. Deep field surveys from telescopes like Hubble and JWST are now providing this exact data, capturing snapshots of the void network at various epochs. When scientists compare these ancient voids to the predictions of supercomputer simulations, they find a remarkable agreement. The simulations show a dynamic ecology of emptiness, where voids do not live in isolation. Smaller voids are frequently absorbed by their larger, expanding neighbors, merging to form the colossal supervoids we see today. This is a process of cosmic consolidation, where the architecture of nothingness is constantly being rewritten. The life cycle of a void, from its birth as a faint underdensity to its maturity as a vast spherical region, mirrors the life cycles of the galaxies within the web. Both are born from the same primordial seeds, both grow and evolve through the same forces, and both are part of a grand, symmetrical pattern that connects the universe's past to its present. Watching a void evolve is like watching the universe itself breathe, a slow, deep exhalation that stretches the fabric of space and reveals the hidden rhythms of cosmic time. These silent voids may be hiding the universe's oldest and most elusive objects. Primordial black holes are not born from collapsing stars like their more familiar cousins. They are hypothetical relics forged in the incredible heat and density of the universe's first moments. If they exist, these ancient objects could solve one of cosmology's greatest mysteries, the nature of dark matter. And the perfect place to hunt for them is not in the crowded galactic cities, but in the deep, quiet expanse of cosmic voids. In the dense, chaotic environment of a galaxy cluster, the subtle gravitational pull of a lone black hole would be completely lost in the noise. But in a void where the gravitational field is weak and uniform, even a small, compact mass would stand out like a single pebble on a vast, empty beach. The clean, uncluttered environment of a void offers a pristine laboratory for this search, amplifying signals that would otherwise be impossible to detect. Physicist Bernard Carr has long championed this idea, arguing that any unexplained anomalies in the dynamics of a void, a slight, unexpected warping of space or a strange, unaccounted for motion of a lone galaxy, could be the signature of these hidden, compact objects. How would we actually find them? One powerful method is gravitational microlensing. If a primordial black hole were to drift in the emptiness between us and a distant star, its gravity would act as a tiny lens, briefly bending and magnifying the star's light, causing it to flicker and brighten for a short time. In a void where there are far fewer stars to monitor, any such flash would be a dramatic and significant event, a clear signal against a dark background. Another approach is to scrutinize the motions of the few galaxies that do reside within voids. These isolated galaxies should move in predictable ways, dictated by the large-scale gravitational pull of the void itself. If their paths show tiny, inexplicable wobbles, it could mean they are being subtly tugged by the invisible gravity of primordial black holes scattered throughout the emptiness. Finding these ancient objects would be a monumental discovery. It would not only identify a key component of dark matter, but also provide a direct window into the universe's first second. The existence and mass of primordial black holes are deeply tied to the physics of the early cosmos, to the symmetry-breaking events that shaped the fundamental forces. A void, therefore, becomes more than an empty space. It transforms into a time capsule, preserving a hidden population from the dawn of creation and offering us a chance to touch the very origins of everything. The cosmological principle rests on a profound and simple idea that the universe looks the same in every direction and is evenly filled on the largest scales. This assumption of isotropy and homogeneity is the bedrock of modern cosmology, the starting point for almost every equation describing the cosmos. Yet this very foundation is tested by the existence of the cosmic web, a universe that appears blatantly lumpy and structured. So where does that leave our grand principle? The answer lies not in ignoring the voids and filaments, but in using them as the ultimate statistical probe. If the universe is truly isotropic, then the voids we see should be scattered randomly across the sky with no preferred direction or alignment. Their shapes and sizes should form a uniform, democratic distribution, no matter where we look. Cosmologist Michael Longo has spearheaded investigations into this very question, meticulously analyzing the orientations of thousands of voids from all sky surveys. He searches for a subtle signal, a collective tendency for these empty regions to point in the same cosmic direction, like a vast array of compass needles all tilting toward an unseen pole. Such a finding would be revolutionary. It could hint that the universe has a preferred axis, a fundamental anisotropy imprinted at birth, perhaps even a slow overall rotation. The methods for this investigation are intensely statistical. Scientists use powerful algorithms to measure the three-dimensional shapes of voids, treating each one as an ellipsoid with a major axis, a specific orientation in space. They then plot the directions of these axes across the entire celestial sphere. Under the cosmological principle, this plot should show no pattern, just a random scattering of points. But if a curious alignment emerges, if the voids in one hemisphere tend to line up in a specific way, it would be a crack in the foundational symmetry of our models. This is not just an abstract exercise. Some analyses of the cosmic microwave background have suggested potential anomalies, large-scale asymmetries that are difficult to explain within the standard model. Could the distribution of voids be the missing link, the large-scale structure that explains these background whispers? The symmetry here is deeply philosophical, an expectation of uniformity against which we measure the reality of our observations. By serving as impartial gauges, these great emptinesses become the guardians of cosmic fairness, ensuring that no direction in the universe is fundamentally special. Their silent, statistical testimony either reinforces our most basic assumptions about reality or forces us to envision a cosmos that is far stranger and more directional than we ever dreamed. These silent bubbles of emptiness are a direct line back to the universe's first and most violent growth spurt. The quantum jitters that inflation magnified to cosmic scales did more than just seed galaxies. They also carved out the blueprint for the voids. This means the pattern of emptiness we observe today, the specific arrangement and sizes of these cosmic bubbles, is a frozen record of the physics that governed the inflationary epoch. Inflationary theory makes precise predictions about the nature of those initial ripples. It suggests they should be almost, but not perfectly, scale invariant, meaning the strength of the ripples was nearly the same across all different sizes. This slight deviation from perfection is what cosmologists call the spectral tilt, a crucial parameter that tells us how the energy of the inflaton field, the engine of inflation, changed over time. The statistics of cosmic voids are exquisitely sensitive to this tilt. A universe with a slightly different tilt would produce a completely different distribution of voids, some with far more numerous small voids, others dominated by a few colossal supervoids. As expert Aikaro Komatsu explains, by carefully counting and measuring the voids we see, we can tightly constrain these inflationary parameters, effectively reading the settings of the universe's birth from the pattern of its emptiness. This connection goes even deeper. Some of the most compelling models of inflation involve not one, but multiple fields driving the expansion. This multi-field inflation can leave a distinct signature in the cosmic web, potentially producing specific features in the void population that single-field models cannot replicate. For instance, a small bump or dip in the inflationary power spectrum, a feature that would be subtle in galaxy clustering, could be dramatically amplified in the statistics of the voids. A sudden excess of medium-sized voids, or a curious gap in their size distribution, could be the telltale fingerprint of a second field at play during the universe's first moments. This positions these great voids as more than just empty space. They are relics of the primordial symmetry breaking that occurred during inflation, the moment when the fundamental forces of nature froze into their current distinct forms. Every void is a fossilized bubble of that primordial epoch, a pocket of spacetime that preserves a memory of the universe's most explosive instant. Future surveys like those from the Vera Sea. Rubin Observatory will map millions of these voids with unprecedented precision. By analyzing this vast catalogue of nothing, we will not just be studying the architecture of the modern cosmos. We will be conducting archaeology on the moment of creation itself, using emptiness to discriminate between the different stories of how everything began. Our journey through the cosmic voids reveals a universe where emptiness is not a void of meaning, but a canvas of profound symmetry. We have seen how these great nothings serve as pristine laboratories, testing the limits of gravity and magnifying the whisper of dark energy. Their hierarchical structure, a nested set of bubbles within bubbles, echoes the scale-invariant ripples from the inflationary dawn of time. And through their precise statistics, they calibrate the fundamental parameters of our cosmos, confirming a deep and underlying balance. This exploration transforms our very perception of emptiness. What was once seen as a mere absence is now understood as an active, structured component of cosmic design, a silent partner to the brilliant galaxies. The hidden symmetry these voids reveal connects the largest scales of the universe to its smallest quantum origins, showing that the rules governing the everything are perfectly mirrored in the nothing. Carl Sagan's timeless words ring true: the cosmos is within us, and in understanding these vast emptinesses, we find a key to understanding everything, a reminder that our quest for knowledge is as much about the spaces between as it is about the points of light. What do these cosmic deserts make you wonder about our place in the grand scheme? Share your thoughts on these mysteries in the comments, and subscribe for more deep dives into the enigmas of space. Together, let's keep exploring the symmetries written in the stars and the profound voids between them.